Hello, everyone. Welcome to SNIA, the Storage Networking Industry Association's Performance Benchmarking presentation. This is the first in what we hope to be a series of back to basics fundamentals for storage, including obviously the performances and packet walks and new technologies and new protocols. And today we're going to be talking about the basics and fundamentals of performance benchmarking. And we're really excited to be able to walk you through a lot of these terminologies and taxonomies and questions that you may have. Today we are going to be doing the presentation from a variety of different sources. My name is Jay Metz. I am an R&D engineer working for Cisco on storage systems, and you may have heard my voice somewhere in a previous Bright Talk webinar before. And today we're going to be having a real treat with Mark Rogoff, who is from EMC. And Mark is an IT professional, career spans over 20 years, 7 companies and 2 continents, and a few languages as well. He's been at EMC for about 11 years as a NAS subject matter expert, and these days Mark works in pre-sales and continues to do an awful lot of these kinds of things, working very closely with the technology and education, and represents EMCs at trade shows as a speaker. And we also have from NetApp, we've got Ken Cantrell, and Ken began working on CC NUMA-based server performance issues, so obviously right along the same vein as the topic. In 1997 for Data General, and as a professional, he's transitioned from SAN to SAN and then NAS performance analysis, and even though he's been working with the internal performance efforts, he's traveled extensively and delivered a lot of training on SAN and NAS performance topics to the field and of course to customers. So about 8 years ago, he became a manager, but we're not going to hold that against him in this fact, because he actually does know what he's talking about, with no apologies to managers everywhere, and remains active in his engineering, including representing NetApp with the storage bodies. Without further ado, let me pass the baton back on to Ken. Oh, one quick question for a little bit of housekeeping. This is a SNIA presentation, the Storage Networking Industry Association, the Ethernet Storage Forum, and as a result, all the material contained is copywritten by SNIA. You will be receiving a copy of the presentation after a couple days. It'll be posted with the corresponding blog on the SNIA Ethernet Storage Forum website. But we would like to give the typical disclaimers of, no warranties expressed or implied, and get your own Cutco knives in order to cut your can of tomatoes or whatever. Either way, we will have the presentation for you a little bit later on. So enough of me, and on to Ken. Ken is going to start us off. Please, Ken.
Thanks, Jay. All right. I think as we start, we probably ought to address the fact that I'm from NetApp, Mark's from EMC, and we're co-presenting something on storage, which is a little unusual, perhaps. A lot of people would consider us to be rivals. So, Mark, what's up with that?
Hi, everybody. My name is Mark Rogoff, and yes, I work for EMC, and this is interesting how we work together. But the answer of why is really, really easy. The fundamentals of storage performance benchmarking are exactly the same, regardless who the vendor is or what the product is. There's benefit for everybody, for our customers, for our products, for our industry as a whole, if we approach all of this together from the same direction. And we're using the same language. And that's really why we're doing it together.
So I think we ought to set at least one more thing. There were a huge number of people pre-registered for this. So I think as we get started, we ought to make sure that expectations are set well, because there's a lot of things that people could be expecting from a presentation like this. So what are we going to cover? What are we looking at today?
Well, today we're presenting the first in what we hope going to be beginning of a short series on benchmarking and performance benchmarking specifically. And in this first session, we want to work on creating a set of common expectations and the language for benchmarking. By doing that, the theme of today is metrics and terminology. So we will walk over the terminology. We will walk over the differences between block and file. And we sometimes refer to them as SAN and NAS, if people really care about. But we will also have some fun. We'll hope to have some fun again with something that we call the graph fun section, when we will go over and just show you a couple of graphs and show you how interpretation changes.
And really, that's where this presentation is working up to. The graph fun at the end and walking through metrics is really where we're trying to work the whole presentation to, I think. So if
the point is of those metrics, sorry that I interrupt there, is to show that the infamous independence comes from. We want to show how, when people look at the performance metrics in the graph, why they say independence. What do they mean by that and where it comes from?
And if you are on the call, you're an expert in the area, you will probably notice there are areas where we're simplifying, and we're doing that on purpose because it is meant to be a foundational course. If you have questions about it, feel free to send the questions in on the question line. We'll try to answer them later, but we are aware that there are places where we're kind of simplifying. So let me kind of jump right in here with what we call the 3 great buckets of testing. So I think the goal for most people in performance testing is you would really want to test in your business environment if you could, because the goal is really to understand how is my storage array going to perform in my business environment, doing my business applications, doing my business workloads. The problem, though, is that if you really want to experiment with that, try different vendors, try different workloads, try different configs, it's really, really hard to do that in the business environment. It's really expensive, it's very time-consuming, and quite frankly, it's just hard. So what we tend to see, and I'm going to use this word pejoratively, negatively, a lot of people don't, but we see people swing the pendulum all the way over to what I'm going to call bake-offs. And the idea here is a great idea, that you take 2 systems, you compare them head-to-head against each other to decide which one is better. The problem is that when people do that, they tend to do this, they tend to do something that they have the time, the expertise, the money, the equipment for, and that, unfortunately, often doesn't represent what their business needs. So you end up with this single obscure metric that doesn't necessarily refer to what your business wants to do at all. So an example, people will do a single-threaded copy, like they'll do a Windows drag and drop or a Unix DD, and claim that this one little test is going to represent the performance of their enterprise storage system in their real business environment.
Well, not to claim that that's never going to be true. We can potentially come up with some business solution where single-threaded sequential writes and reads still going to be applicable.
You're absolutely right. The problem, I guess, is when it's not. You have a database environment or a VDI environment or a compute farm, and you're doing something very, very simple.
So it's when people have expensive storage solution, they go out and they don't spend any money or thought at all on their tool, and they go out something for free like Unix DD or Iometer. Not to say that they're bad tools, are they?
Right, and that's an important thing. I'm using bake-offs in a bad way. Those tools underneath can be fantastic tools. BDbench, for example, is a great tool that's used to underlie at least one industry standard benchmark. But the tool itself doesn't create a useful test necessarily. It's how you use it. And that's really where we want to transition to here, is the idea that there's got to be something bridging this idea between a bake-off and a business. And we're going to suggest that that idea is a benchmark. So what we're talking about today are benchmarks. I like to define them as well-defined tests run in a well-defined environment with a well-defined expectation of what you're going to get in the end. But the idea is that it's something that's trying to give you the business metrics you need that represents your business needs. And so that's really what we want to talk about today. And we've got a few listed here. They come from different organizations. SPEC is an organization that produces the SPEC SFS benchmark, which is a NAS benchmark. We'll talk about NAS in a minute. SBC1 is a block benchmark produced by the SBC. There are other benchmarks, but the main idea is that we're using benchmark as a good thing to represent a workload that your business cares about. If we're going to talk about benchmarks, though, I think we have to do it and make sure we all use the same words meaning the same things. We've got to have the right vocabulary to talk about this.
So before we go anywhere further about explaining anything else, we will focus on the terminology.
Exactly. So let me transfer it over to you here for a second to start us talking about block and SAN terminology.
So what we see here in this picture is a simple representation of block environment where we have a pipe or a medium of some sort that carries our packets that have IOs in them from an initiator to a target. So the initiator in this case is a host. Target is most likely going to be a storage array of some sort. And as those IOs are being carried, each IO stands for input-output and an input-output operation. What's interesting about the input-out operation is that block protocols, fiber channels, iSCSI, FCOE, things that we have here noted that describe this relationship, actually have a lot of other operations, a lot of operations in them. But what we have here, we actually went out there and looked at the specification for SCSI4, and we pulled out all the SAN operations they are and presented them in this visual form and highlighted that really there's two operations that are very, very, very important, the read and the write. Am I correct, Ken?
Absolutely. And now I will point out that historically, if you were to approach a SAN performance engineer and ask them about what operations matter, historically what they're going to say is reads and writes. The world we live in today with virtual machines are introducing lots of new operations, some of which have a huge performance impact.
Like unmap.
Like unmap, or SIN provisioning commands, the copy offload commands, and they matter. But still, when you talk to most SAN performance engineers, when you talk about what operations, what IOPS are happening, they're thinking reads and writes.
So let's flip the slide. And you said IOPS, and this is a terminology that I haven't necessarily gone to yet. But when we count every single IO passing through some point on the protocol, and we count those per second, we get the IOPS. It's simply a number of those packets that went through. Each one of those packets is going to carry an operation. And when we talk about IOPS in the block or SAN world, just like we said in the previous slide, it is about reads and writes. So we talk about IOPS, we expect reads and writes in them. We really kind of don't count necessarily all the other operations because you're not going to see them that much. IOPS is also known as throughput. It has another term that people use all the time. So you can sort of use both of them in the SAN world interchangeably, even though Ken and I both agreed that we should stick with IOPS. So let me explain a little bit more about IOPS. The IOPS have a little interesting property about them. And that property comes from the fact of where in your environment do you measure the IOPS from. So if we have here 5 different hosts talking to a storage controller, each one of them doing some sort of operations. The hosts themselves, each of the hosts themselves, is going to see some number of IOPS, and we're going to measure the communication between them and the storage system, and they may see different numbers.
Yeah, in a well-defined benchmark, I think, we're probably wanting all of the hosts, the clients, to do the same amount of work.
Probably.
Maybe they would all be doing 5.
But that's not a requirement. It's a consequence of a well-defined benchmark. But in the real production environment, you may have some clients that are doing a lot of operations, some clients are doing not so much operations. The important thing is if we measure IOPS at the host, we're going to get one number that may not necessarily be representative of the number of IOPS that we get if we measure it from the storage controller's front end. And the front end is a term that we use explaining the side of the storage controller facing the hosts.
So what you're telling me is that the front end really is aggregating the IOPS across all the clients.
That's correct.
Because they're all coming into it. So if I measure at a client, I measure at the front end of the storage controller, I'm going to get different numbers.
That's right. Interestingly enough, when the storage controller is translating the conversation with hosts to its own drives underneath it, something that we refer to the back end, the back-end number of IOPS may be completely different from the front end. And the back-end number of IOPS is going to have the same aggregate property of the IOPS that underlying storage drives would see. And you see here the drives are somewhat similar to the host because they're going to see different number of IOPS in themselves, depending on how often the information is in there or what kind of drives there are, the capability. All of that is going to be added together to produce some sort of an IOPS. So if you get some sort of a measurement, somebody talks about the IOPS of the system. It is important to realize where that IOPS measurement was taken so that when you do compare the two solutions, you measure them at the same point to have an adequate comparison.
And that's a theme I want to hit on over and over through this, that a lot of this is about consistency. that if you're using two different applications to measure IOPS, they need to measure them at the same place, report them in the same place. You're looking at two different vendors, make sure they're reporting IOPS from the same place, because where you measure the IOPS matters.
Along with IOPS, there's a flip of the coin effectively with terminology. It's something that we call megabytes per second. Megabytes per second is a measure of adding up all the payloads of all those I/O packets that are passing per 1 second over this one point in the pipe. And that's what we measure, how much data has been pushed through. Sometimes we refer to megabytes per second as bandwidth. So we can talk about a bandwidth or a throughput, and each one of them is going to mean either IOPS or megabytes per second. And interestingly enough, both of those are sort of flip of the same coin, which is why we have them very closely together. But it's interesting, when I see megabytes per second, and Ken and I both smile at it, there's something that Ken wants to share with you people about that.
So this is kind of a pet peeve of mine, in that megabytes per second is the term that we hear almost all the time. But technically, megabytes per second is a decimal representation of numbers. So if you look at a kilobyte, that's 1,000 to the first. A megabyte is 1,000 to the second. That's different than a mebibyte or a kibibyte or a gigabyte or a tebibyte. Each one of these are in base 2. And that becomes really important, because up at the high side, say looking at tebibytes versus terabytes, there's a 10% difference in those numbers. And it's relevant because in a networking world, we're actually, when we say megabytes, we mean megabytes. But in a storage world, in the computer world, when we talk about PCI buses, or we talk about the size of memory, we talk about the size of the disk drive usually, those are all actually in the binary side, and really should be talked about as being mebibytes or gigabytes or terabytes.
So this is the reason why if you go out there and you buy a drive, internal drive for your computer, and it says 1 terabyte, and you format that drive and it comes out and it's a lot smaller than 1 terabyte, it's because of this notation problem.
At least in part. And what makes it even trickier is that that's an OS-dependent thing. So all Windows systems are reporting them in binary. Some Unix systems now report them over in decimal.
Like Ubuntu.
Like Ubuntu. So the important thing here is the same as we mentioned before. It's about consistency. It's important for people to recognize, especially if they're comparing different tools, they're comparing different vendors, to know, are you reporting it in megabytes, true megabytes per second, or are you reporting it in mebibytes per second? And are they labeled correctly? Because that's one place we sometimes see people getting false comparisons, is they're labeled the same, megabytes per second, but in actuality, one of them is a mebibyte per second.
And the practical implementation for that would be if you're counting a potential of a physical line to be transferring data, you need to understand how that line is measured. If it's 8 gigabits line or 10 gigabit Ethernet line, you need to understand how those metrics are so that you can transpose them together.
Okay. I think you've got one more term person.
We got a couple questions to that end that I think might be useful to pause and answer, because I think that we can actually segue into the next section pretty quickly or pretty easily. First of all, the questions are involving about the storage subsystems and how the numbers on the front end and the back end are different. And so one of the questions has come up as to why are those numbers different? You know, why are they going to be different? Can you just do a quick clarification? And secondly, how do you define that front end and back end of the storage controller? So the two related questions about the controller itself and the front end and the back end. I think there might be a bit of a confusion about what the front end and back end mean and actually how they interact or how those numbers relate.
Okay. So I'll take the front and the back end real quickly. We will switch the slide back so you have a better visual reference. The front end of the storage controller is facing the client. It's the hosts. It is something that's connecting to the storage controller over typically fiber channel or iSCSI protocol. This is the I/O that the controller is either sending to the host or receiving from the host. The back end of the storage controller is the end that's facing the storage medium. Whatever is the flash drives, the spinning drives, regardless of what that is. That's what the storage controller side connecting to those drives. And the difference, Ken, you want to cover why they're different?
So I think, how do you know which one's which? In general, where your number's coming from. In general, your numbers that we see as customers on the primary interface on most arrays, it's going to be the front end. Because what they're telling you is how many IO operations am I servicing from my clients, from my hosts. The number about what we do to the disk drive is an important one. Lots of times it's important to understand your sizing and how well you're using your disks, using them effectively if you're trying to overuse them too much. But that tends to be a secondary number, I think, in terms of how most interfaces are going to provide you results. So in general, assume you're seeing front-end numbers unless it specifically refers to the I/O I'm doing to my drives.
And then the other point is that the numbers we have here on the screen have nothing to do with reality. They're completely imaginary, and it doesn't necessarily mean that the back-end numbers are always going to be different, larger than your front-end numbers. The difference between them will be organized because of some RAID overhead or the way the environment's been set up. There could be 1,000 reasons why they're different. As long as we understand there are two different points where they're being measured, and keep those points consistent when you compare the two systems is important. So let me switch back to the slide where we left off. So there's a trio of terminology in the block and SAN world, and the third one of the trio is I/O size. So it's effectively how much of the data each I/O is carrying. And with that, we'd like to really show you how the I/O size, IOPS, and megabytes per second relate. And we have an interesting graph that we put together showing the difference. And Ken even wrote down a formula. Can you explain that formula, Ken?
Sure. So what we're trying to say here, it's very simple. That the megabytes per second that you're transferring, or the millibytes, and I like to use millibytes because, like I said, it reminds people of the difference, is equal to your I/O size, how big your I/Os are, how much data you're transferring, times the number of those you're doing in a second. So what would happen is, if you look over on the right-hand side, if you keep your IOPS the same, you're doing the same number every second. If you do bigger I/Os, you get more bandwidth. Let me switch. I'm going to switch one more slide here and talk just a second more. Conversely, if you were to keep your I/O sizes, how are we showing this? We're showing this as megabytes per second. At the same megabytes per second, as the I/O size would increase, your IOPS would have to decrease. So if you're going to keep the same megabytes per second and one term on your right-hand side goes up, the other term has to go down. This is important. I realize it's pretty basic math. It's surprising how many people get the idea wrong, though, I think, because someone won't realize how small their I/O sizes are. They'll be looking at a performance chart and ask, why am I not getting 600 megabytes per second out of my storage array? And it's probably because they're doing itty-bitty tiny little I/Os, and they just can't do that many I/Os. For example, if you look at the blue on the bottom, 512-byte I/Os, right, you can be doing 262,000 IOPS, and you're still not going to be doing more than 150 megaseconds. So just understanding the relationship between I/O size, IOPS, and megabytes is an important idea. And
this also pulls in together with what we said in the very beginning, when we said that if in what we call the bake-offs, in the single obscure metric situation that doesn't give you the volume and understanding that you need to move forward. So if somebody's concentrating on IOPS only in this case and they don't think about the I/O size, they may be confused in thinking that IOPS are important, but they're really transferring data and how much of that data they can carry from one place to the other.
So let's do the last term here we have for block.
So the last term for the block is the very, very, very important one. That's known as response time or latency. And that's a measure of time. Typically we say in milliseconds, but these days it goes down to nanoseconds and microseconds in between, where it's a time that it takes for the target to answer to initiator. So initiator starts some sort of a process, and then target takes its time to answer back. So let's flip the slide and show you a little bit. When one host is doing a write, and what that host is going to see is it sends the I/O to the storage controller. The storage controller processes that I/O, and it takes some time to process it, and then send it back. So if the storage controller processes the I/O for about 1 millisecond, the host is going to see the response time just slightly over 1 millisecond that the host hit. So because the response time tends to be aggregated with all the points within it. So we're going to see this more in the reads. If the host is reading some data from a storage controller, it sends out the request, the storage controller processes the request, let's say for the same 1 millisecond, realizes that the data needs to be read on the disk, goes out to the disk, and reads from that disk. The disk processes the read request in turn as well. It takes, let's say, half a millisecond, and that data is returned back. The host's response time impression is going to be something north of 1.5 milliseconds.
So going back to our front-end, back-end kind of measurements we were just talking about, where we're measuring response time matters. Because if we measure it at the disk, we might see response time of half a millisecond for that. We measure it at the storage controller, perhaps it still looks like a half a millisecond. Maybe the storage controller doesn't have to do much work. But if the storage controller itself is doing work, the client is seeing a second and a half. It was aggregating that. And I think you've got another example for us on this.
Yeah, we have a different example where the host is reading from the slower drive, and the drive takes, in this case, 4 milliseconds to answer back. So with the same math of 1 millisecond at the storage controller, the client, in this case, is going to see north of 5 millisecond response time. It is the same storage controller system. It is the same set of clients, but again, just like Ken said, where you measure response time and IOPS matters, and their aggregate property of response time is something to be dealt with. Remember, what host sees is a sum of response times of everything in the chain going forward.
Okay.
And I think this covers more or less everything we wanted to talk about on block.
So let's transfer to file and NAS. And I know we're moving fast. The nice thing is this is recorded, so people can go back and listen to it 3 times. File and NAS technology. So I'm going to move maybe even a little faster here, because a lot of the ideas that we're going to talk about here are exactly the same ideas we talked about with SAN and block. But some of it's going to change just a little bit. So NAS stands for Network Attached Storage. In this world, instead of having targets and initiators, we have clients and servers. And our transport is now something like Gigabit Ethernet, for example. And our protocols are switching from being fiber channel, FCOE, iSCSI, to being file and file system oriented protocols like NFS, SMB, and FTP.
So the big difference here is that the file accesses files.
It does. And so what that means is that it's really, instead of talking about these IOs, we're now talking about ops. We're talking about things that allow us to open files or close files, set or retrieve the attributes of files, create files, delete files, walk through directories. For example, we'll look at the one for NFSv4. There's a lot of operations on this table, because there's a lot of operations in NFSv4. But none of them are big. And you made my chart for me. Why? Why is everything the same size?
Well, Ken, they're the same size because unlike block, where read and write are dominant, in file, it is very common to see a huge mix of other operations as well. Nearly all of those operations affect performance. So in NAS, even though in some cases we still have reads and writes, they don't necessarily always dominate the picture. And that's why, by the way, we don't use IOPS in the file. Oh, these, by the way, the second slide here is the SMB3 operations, which are there's even more of them than compared to NFSv4. And again, every single one of those operations matter.
And exactly like you said, it's why we tend, in a file world, to stop talking about IOs, because IOs tends to imply this idea of reads and writes, when we're talking about ops instead. And we stop talking about IOPS, and we're now talking about ops. We're counting the number of operations per second at a certain point on the log. We also talk about megabytes per second. Just like we did with block, we're also talking about megabytes per second. Although it's a little different, because in the block world where we talked about megabytes per second, we were talking about the amount of I/O transferred primarily between reads and writes. And in the file world, we're talking about the amount of data transferred by all of the operations. And that's a tricky one, let me say, because not all vendors are going to report in a NAS world megabytes per second being all operations. Not all tools do. But for a lot of tools in a NAS world, when we talk about megabytes per second, it's reads and writes and the payload for things like a get attribute call. And we'll talk about that.
And then you have 2 other things, bandwidth and throughput.
I do.
It's a little different than it is in the block world, isn't it?
It is, and I'm going to tell you, just don't use those words.
This is a very interesting recommendation. Why exactly is this happening?
Well, in a NAS world, I have seen, so bandwidth is almost always referred to as just megabytes per second. But throughput sometimes is ops, sometimes throughput is megabytes per second, sometimes throughput is something else entirely. Those terms, and sometimes throughput is supposed to mean bandwidth, sometimes it's just confusing. And so my recommendation, my strong recommendation would be stop talking about bandwidth and throughput in the NAS world and just refer to ops per second and megabytes per second, or, more appropriately, millibytes per second.
So let's illustrate a little bit.
Well, hang on, to that end, there is a question that comes in that's pretty topical in that regard.
Sure.
Specifically about the ops per second in NAS and the composition of them out of the ones that you were showing. Can you go a little bit deeper into the composition of the ops per second that you were just showing?
I'm going to do it without going back into the slide deck.
Yeah, we actually have a little bit of a graph that we'd like to show.
Okay.
If that's the only question, we will continue on and address it, or we'll take another question.
I think we can do it really quick. I think in what you're seeing in a file world is you see sequences of operations to access a file. So if you want to read a file in a file system, you first have to learn where that file is. So you'll have a command that will say, go into this directory, get me a list of all the files in the directory so I know if my file is there. And so and that'll generate, like in an NFS world, that'll return you a file handle. Once you have a file handle, then you can actually do a read request to read data from the file. It's a little different in an SMB world because it's stateful as opposed to stateless. But the idea with both of them is you have complex sets of operations because files have to be found before they can be read or they can be written, and you want to do things to them. Like every time you read or write a file, you generally change its modification or access time. Those are separate calls. And so you see a lot of operations like that in a NAS world. And they all take processing time at the file server.
So before we move on, we still have response time and latency in the file world as well, and the idea is exactly the same, isn't it?
It is, and both of those words we tend to use, you and I, we use interchangeably, and we see the industry using interchangeably. It means the same thing. Instead of the target initiator, it's now the server replying to the client, but all the same things apply. And with IOPS and megabytes per second, they apply to where you measure matters. All
right, but let's show how operations per second and megabytes per second relate together.
Yeah, and this is a good one. You kind of implied this a second ago in that it helps understand the mix of operations. So what we have here, we have two otherwise identical runs with different, or tests with different NFS operation mixes. If anybody cares, it's a 64 kilobyte IO size, but everything's the same on this, except in one test, we did a lot of stat calls. We got information about the file. And in the other one, we did a lot of read calls. So we just switched the percentages back and forth between those two.
And for people who are not familiar with what a stat call is, you can think about it as you're just tapping something on the shoulder saying, who are you? And the person responds, and then you sort of look inside of them. That'll be the read call.
Right. The workload that we're doing is trying to do about the same number of operations. It's just changing the mix of whether or not we're doing more stat calls or we're doing more read calls. What we see in that is very interesting. Now, your results, if you were to try to reproduce this, your numbers are going to be different. Because the faster your storage array, the faster your client, it might change your numbers. In our test, as we did that, what we saw is that you get a lot more ops by doing high metadata operations, and a lot fewer ops when we did high data operations. In our test, that's because our client had a tendency to cache those metadata operations. They never actually went back to the storage array, so they were really, 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 really fast.
And then, in all essence, a stat call is easier to answer than a read.
It is. And that's we talked about the difference between IOPS and megabytes per second, right? Those read calls are bigger, which means you can't do as many of them as quickly. And so we see fewer of them happening. Looking at it a little differently, though, if you look at it megabytes per second, then we see something very different. And
we kind of split them here, didn't we?
We did. So we actually see about the same number of read operations, the amount of data transferred by the read operations is roughly the same, not quite the same. You get more on the high data operations ones, but not probably as much as you would expect because they're taking, our storage array can only do so much at a time. But we see a lot less data transferred by those metadata operation mixes. So what's the point of this, Mark? And why am I going into this?
Well, I think we're trying to illustrate just two different things, and this particular example does a good job. In the file world, operations matter. So these two mixes represent these very two different potential mixes for applications. You may have an environment that we commonly require to talk about as a software build, where there's a lot of what we call metadata operations, things like stat, things like what's the security in the file, can I write through it before we actually have some data passing through. Or we may have a representation when there's a lot of actual writes, something like a database, where a file is really, really huge and all the application does is reads and writes and nothing else. And it's very dangerous and wrong, very wrong, to be comparing those two against each other.
So really, what I've done here, comparing a high metadata operation mix and a high data operation mix, it's just a bad idea. They're different workloads representing different business needs or applications, and I probably shouldn't compare.
That's right. That's right. You shouldn't be comparing them one against another. You just have a system that we've tested here. We know how it behaves during the high load of metadata operations, and you know how it behaves during the high load of data operations. But it's simply comparing operations per second is the second point I'm trying to make here, or ignoring other metrics like megabytes per second is deceiving.
So we get a different story about the value here, or what these workloads do. We look at ops versus megabytes per second.
Very true. So let's explore the graphs and explore the subject a little bit more and play our favorite part of this presentation, the interpretation game.
I love this. So what we're going to lead to is it depends, right? I think we're going to get there quick, but let's start off slow. So I have here results from two different systems. Okay, we've agreed about what our operation mix is. We don't have any more concerns like we did on the previous slide about having two different operation mixes. I have a single operation mix. Everything is the same number of clients, same network. I've done everything I can to make these things the same.
And we measure those IOPS exactly at the same point.
And I measured them in the same point. But I have one system that's giving me 10,000 ops a second, one that's giving me 5,000 ops a second. What I want to know, Mark, is what system do I want to buy?
Well, clearly the blue system number one, is better because it does more IOPS in this case. Isn't that really, really clear from this example, Ken?
And you know, we see lots of charts where people would say that's exactly true. The fun part is that clearly it's not clear. So what I've done is I've added a response time y-axis now. So my x-axis is exactly the same, but I've added a y-axis of response time, showing that System 1, that was doing 10,000 ops, is still doing 10,000 ops, but at a response time of 10 milliseconds. System 2, which was doing 5,000 ops, is doing it at 5 milliseconds response time. So now let me ask, what system do I want to buy?
Well, it's funny you brought it to here just by adding another access point, but I have to say it depends. It kind of appeals to me to have a system that does operations quicker, but I don't like that it doesn't do as many operations as the other one. So what I really would want to look at this now between these two systems is I don't think I have enough information here. I need to see more load points, as we call them, and compare them better before I can answer where the one is better than the other.
We can do that. So here what I've done is show a chart where those 2 points, the pink one, peach one, whatever this is, and blue are the exact same points I had before. They're the same response time as before, but they're now represented as just 1 point on a curve of performance results. So in most benchmarking situations, someone's going to take the load, the amount of work they're asking the storage array to do, and they're going to crank it up somehow. Maybe they ask their threads to do work faster. Maybe they create more threads all doing the same amount of work. But something they're going to do is going to ask it to do more and more and more work. And we tend to chart those as a continuous line showing it. So
what's interesting I see here, Ken, is that what you've done here is you gave the two previous measurements we've played with were taken at a different point from a different IOPS point of view, which is confusing, even though you may say this is the points when the plateau measurement of these curves is ending effectively.
You're right. So let's just get rid of the points. Okay.
If we get rid of the points, I think it's going to be fair enough for me to look at them. And when I compare the two curves here between them, and you still ask me the same questions, I presume?
Yes. The question is, what system do I want to buy?
And the answer is, it depends.
It depends on what? Clearly, right? That pink one is much.
Well,
better,
here's how it depends, Ken. When you look at the environment like this and you look at the results like this, you really need to assess of what your production environment application needs to do. What if your maximum performance need that you will ever expect your production application to do will never cross north of 4,000 IOPS? And if we assume that, and then we really cut off all the other ends of these curves from the right, we only concentrate on what's shaded area, and we compare them then, well, that's when System 2, the orange one, is going to win over System 1, the blue one, because it responds a lot quicker.
So you're telling me, just to be clear, because this is kind of a message we want people to hear, your business needs are going to dictate really how you interpret a chart like this.
Absolutely. Absolutely. Conversely, if the business needs are a little bit different, let's say normal businesses would expect not a maximum point, they will just set some sort of a minimum. So let's say we set the minimum at 10,000 IOPS. And if they're set at 10,000 IOPS, the orange system, System 2, is out of the equation whatsoever. It doesn't even satisfy my minimum requirements. And therefore, it's not necessarily correct to compare them. Blue system is the only one that wins.
So again, my business needs completely reinterpreted how I saw that chart. If I had a minimum performance need versus a maximum performance need, I might end up with a completely different buying decision.
That's correct. That's correct.
Now, it's been interesting. I think over my career, I've seen something at the transition taking place. People they still care about throughput, like we've shown here. Oh, I said throughput. I'm a terrible person. They still care about ops, right? Just like they have been. But they also care more and more and more about latency, about response time.
And what's interesting about response time these days, and my add to that, is response time doesn't necessarily come as a max or a min. It comes in as a band. We expect the response time to fall between certain numbers.
That's true. I think if you get better response time, most of the time people might be happy, but you certainly have here's the response time I want, and you can't vary by more than that.
Absolutely, but sometimes you have SLA agreements written where the bounds are defined.
You certainly do.
So what we see here now, I presume you're still going to ask me the same question as before, right? When we have an acceptable latency band painted over our lines, which one of these two systems is better?
Hey, even I can answer this one.
Okay, go ahead, Ken.
It's System 2. System 2 is the only one that fits in my latency band.
Well, it depends, Ken, and here's why. So when we were measuring these systems, one of the things that we noticed is that the number of load points is not great. So let's throw in more load points. Let's see how the system behaves over much smaller intervals that we're averaging out to get to the response time calculation.
So instead of, for example, charting 5-minute averages of performance, we're now charting, say we're doing 1 second or about 15 seconds here.
So we're going a lot deeper into the environment we see. And what's interesting here, Ken, since you started asking questions, we see the picture like this. And now, with more load points on them, we realize that we see what we see. So now which system is better and which one you would go with?
Well, if my acceptable latency band is purple, even though the average of my System 2 matched and it fit in that band, I can see that looking at it more granularly and at a much more frequent basis, it doesn't match. Even that system isn't going to meet my business.
Because it blows on the top out of your acceptable band. So the ones where it goes on the bottom, it's kind of okay.
Probably okay.
Probably okay, but the ones that go on top is not okay. Now, we have the term that we have on top of the slide called variance. And what we define with that term is exactly the amount of changes between those values as measurements go along. So the variance of the blue system, System 1, is a lot better than the variance of System 2 across the entire measured interval.
And there are some business applications that even if the average for System 2 was better than the average of System 1, it may be that having the reduced amount of variance is a better thing.
So in other words, somebody was interpreting this graph and they're saying how my business application requirement is laying on top of it. They may still go with System 1 even though it doesn't fit the acceptance latency band, just because it's more predictable in its variance.
It's all about what your business needs, right? What your business requirements are.
Well, are there any other metrics that the business really cares about, Ken?
Actually, I'll turn that back to you.
Well, I wanted to hear yes, but one of the popular metrics that we see people care about is something like the dollar per op. And we actually hear this more and more when we discuss different products, is this system is cheaper per dollar per op or more expensive. So on our two systems that we're still playing with and comparing, we kind of said the blue system is $10,000 and the orange system is $50,000, and that's where the numbers sort of come from. And if we measure them at 5,000 IOPS, it's $2 per op versus $10 per op on these two systems. But what's interesting is that these additional metrics change when you start measuring them at a different number of IOPS. So at 9,000 IOPS, the numbers are now 5.5 and 1.1. So it's kind of difficult to talk about which one of them is better because we haven't necessarily always keep the context the same.
Jay, I think I may hear you trying to break in on us. Did you have a question?
Well, it's there are a lot of really good questions in the chat window actually, and unfortunately some of them are a little bit more advanced than what we can talk about. But it sounds like the "it depends" mantra is echoed within the questions itself. But one of the very interesting questions that came up was when you're making a system that's going to be used by multiple customers and you don't yet have an accurate business need response time range yet, what kind of evaluation criteria are acceptable in that case? I mean, because if we're talking about so many interdependencies, especially when it comes to the dollar signs, and you don't actually have that business need mapped out, how do you prioritize?
All right, so let's continue with this theme, and we'll finish a couple of slides, and then we'll come back and we'll answer that question a little bit. So on the metrics, other metrics to consider. So there's other things besides dollar per op. It could be dollar per watt, or dollar per rack U unit, or something else. The important thing that we would like to carry forward is that all of these extra metrics, they matter at a very given context. So if we're measuring things at 9,000 IOPS, then the orange set of numbers matters at 9,000 ops at 17 milliseconds. That's when those numbers make some sort of sense. The blue numbers also matter at 9,000 ops, but at 10 milliseconds, because it is the context that defines metrics and makes metrics matter. And that's probably the most important point of our graph fun section. We would like to pass this forward. When you measure something and you don't know how it's going to get used, the ultimate conclusion is going to be affected tremendously by the context in which you're going to put it in.
And there's at least two contexts, right? There's your business needs, where we're focusing a lot, and then there's the technology context, I guess, as well. But what is this thing that I'm measuring, and how do I interpret it? But it's all about what is my business need. So your question that was passed up, how do I know what I care about if I don't know what I care about? I mean, I think that's a one way to rephrase that. Is it really? I don't know that you can give a single pat answer to that. In that, if you don't yet know what your response time metrics are, perhaps you know at your business level what my bandwidth requirements are going to be, or what my growth expectations are going to be. And in that case, maybe what you do is you get a test system, you put the best equivalent of your production environment on it that you can, and you see if your clients are getting the appropriate level of response times, and then try to work out, okay.
Well, let me simplify this, Ken. I would say that the really infamous answer to that would be it depends. But the whole point about it depends is that it depends on the business use. That's the full sentence that people sometimes forget to mention when they drop in it depends when you ask them a question like this. It's meaningless to measure something without knowing how it's going to get applied, because it will depend on the application.
That's a great point, and I think that's when we started this, and you and I had table conversations about what is it we want to talk about and what do we want to present. That idea of people measuring stuff for the sake of measuring it, as opposed to measuring things to make a business decision, what was something that came up a lot. That you and I had both been in bake-offs where somebody at a technology level said, I think this would be really, really cool. And if you pushed them for what are you going to do with that data if you had it? That by the way, somebody told me that years ago. I use that question all the time. What would you do with this data if you had it? When you come back to them and you ask them that question, they realize I have absolutely no idea. So I think part of that is unless you know what you'll do with it, may not be relevant.
So take this away, guys, what we see right now on the screen. The context makes the metrics matter. And let's summarize a little bit of what we have so far.
So at this point, we've tried to walk through terminology, not just for terminology's sake, right? But because we all use the same words to mean the same things, then we have a better chance of having meaningful conversations together without confusion. So as we did that, we tried to talk about ops versus IOPS, about megabytes per second versus millibytes per second, about latency and response time.
So let me do a quick reminder. Megabytes is base 10, millibytes is base 2.
It is indeed.
Something that if you don't remember what it is, or you still are confused about the two metrics, just remember base 10 and base 2, and hopefully you know how to power numbers.
Or Wikipedia.
Or Wikipedia, that, yeah. The point we're trying to come across is the difference between them grows as you start increasing those zeros behind the numbers. So at a terabyte, tebibyte number, it is 10% difference. Tebibyte is 10% larger than a terabyte. And that becomes very important. You calculate something that you don't know which metrics was used when.
And similarly, our diversions, I guess, as we went through, is talking about IOPS or OPS. They both, that it would matter. Where you measure matters. Response time, where you measure matters, partly because it's aggregated, that it's the response time of every component that's downstream from it as well. And then we tried to put all that together in the context makes metrics matter system with the graph on, which, I love. I love that section. I'm probably going to use that section for internal training. Just to make good points.
We were surely both going to use it now. It's a great one for whiteboarding, guys. If you ever have to explain this to anybody else, try to whiteboard. It takes about 3 graphs on the whiteboard to start going from 2 points to 2 axes to continuous points, and then thinking about the borderlines.
And we did all of it, or at least we're trying to do all this in this context of a bridge, right? The bridges between really, really, really valuable testing and production environments, which is just incredibly difficult to do. Useless, nearly benchmarking sometimes where you're looking at a metric that doesn't really matter in a business environment, test environment that doesn't look anything like your production environment, which I call the bake-off, and benchmarks in the middle. And so we have a term up here we haven't talked about at all yet, and we're not really going to dive much into detail on it, but I wanted to throw it out because you and I are both members of the spec committee. We were both part of making the spec SFS, which is the NAS benchmark right now for spec, the spec SFS 2014. And we would put that forward as a benchmark that tries to put all this together. Right.
It is the bridge.
Exactly the bridge. And one of the things, we don't have a slide on it, but one of the things that spec does is it tries to use business relevant metrics. So instead of talking as much about ops, it's trying to use the language of business in it. So we don't have a link here, but I would point people off to www.spec.org to learn more about spec SFS. Not as the perfect benchmark that exists in the world, but as a good benchmark helping to illustrate some of the principles that we've talked about. This is
definitely one of the approaches that we hold dear for ourselves. Not to say that there's other benchmarks that don't do the same thing.
And then,
so to kind of go on, summarizing this a little bit going forward, as we said, this is the first webcast on the subject of performance benchmarking for storage. Today, our focus was metrics and terminology. I really hope that using the slides that you can download for this presentation, you'll be able to understand and memorize the terminology better, and you'll be able to follow somebody else explaining what is it that they're presenting using this terminology easier. Again, we're aiming this presentation for somebody who's new to the subject. So if you're an expert and you know these terms and you know them by heart, you probably know that some of the stuff that we went over here is a lot more complicated than we painted. And that was on purpose because we're trying to introduce people into this area. We're going to get a lot more, gradually more deep on the subjects on future webcasts. Things like system under test. We would like to explain how the storage arrays are put together. Things like caches. Things like front end and back end a little bit more. We would like to talk about file and block components, like file systems and dependencies there, or what the RAID groups are, or the new methods of breaking information without RAID groups these days. And the coup de grace of it all, the workload definitions. We kind of mentioned this a couple of times during the presentation today as a single-threaded sequential workload. And if somebody is not in the performance game, they probably don't know what we're talking about. So we will be talking at the end of this whole entire thing about workloads. So stay tuned, look into what's going to happen, and hopefully we'll talk again. Jay, passing this to you.
Great. We have about a couple of additional things to do before we start getting into some of the questions. Really quickly, just remember to rate the session. You can see a little button up at the top that says rate the session. And the material will be posted on the Ethernet storage forum for SNEO website and also available on demand at the website listed there. A full Q&A from this web class, including the answers to questions that we obviously couldn't get to today because there were a lot of them. We'll try to touch on some of them in the short time that we have now. But we are going to be taking a lot of the feedback that we got, a lot of the questions that we have, and we're going to be applying some of them to the next webcast, which is effectively the second part of this, which goes into a little bit greater detail, as Mark was just describing. I'll leave this slide up here as I go through a couple of the questions, just a little bit of a heads up. Some of these are a little bit outside the scope of this particular session, but will be more appropriate to the next one. But there was a lot of great recommendations about front-end, back-end disparities because of RAID, some really good advice coming in from the readers and the viewers. It was really good about that. A couple of things about some terminology and in your examples. So let me try to see if I can pick something that's pretty important. One of the things that they wanted to know about was how different protocols affect the performance, but I think that's going to be something we can address at a later date. But is there anything different or special about measuring, testing object storage? Because we started with block, we have a file, but what about object storage itself? Is there anything special we have to focus on with that regard?
We actually consciously stayed away from the object storage in this specific session. So if there's an interest for it, we will gladly add it to the list of things we will talk about in the future webcast. Object is the greatest, hottest thing that's happening in the storage these days. And if there's an interest for that, absolutely we'll take it on.
Excellent. Okay. And basically, if you run, we were talking about the bake-offs and stuff, but someone wants to highlight that if you run bake-offs and have a clear success or good enough criteria, and I think that's just a reinforcement of the material that you focus on. There are a lot of questions about the front end, back end, and some of the definitions of terms. And so, really quickly, in the time that we have left, I think what I'd like to ask you to do is just one more time define op. Someone is not clear what op actually means, and once more the difference between I think megabyte and gigabyte was a new term for some people. So if you can just talk a little bit more about the definition of the terms, and I think we can end probably on that question, and the rest can be done in the blog.
Okay. So the first
Operations.
Okay. We're just using the word ops to mean basically operations. So, well, actually we're not. To mean operations per second, right? So we're saying that across the wire in a NAS world, every one of those commands that you're sending from your client to your storage array, whatever that is, if it is a command to open a file or close a file or get an attribute or set an attribute or find a file, whatever those are, and we've got a list of them up here, we're saying that each one of those would be an op. And they are how many of them you are doing in a second are your ops, your operations per second. It's a little confusing sometimes because some people will put an OP and a /S. Some people will just write OPS like we did here. A lot of times when people are using IOPS, IO operations per second, they will simply write IOPS and they won't do IO/S. And so we were using OPS to be consistent with the IOPS terminology.
All right, and the second question was about megabytes and megabytes. But before we get there, so let me clarify. So we're trying to say that ops, operations per second, is a terminology used in file or NAS land because different operations matter at the same time. In the block land, People use IOPS, and they don't really talk about operations per second because it's about reads and writes predominantly. And that's a major difference between the two file and block worlds.
And I will acknowledge, I mean, we tried to do it on the previous, when we went through it the first time. There's a little bit of historical to that in the hyper virtualized world that we're into now, there are more and more stand commands that matter for performance besides reads and writes. And so there are some instances where people are going to be talking about ops and they might mean more than IO, reads and writes.
But they'll still call them ops.
But they'll
distinguish them from IOPS.
They almost always will. And you find anybody that's been kind of talking about SAN performance for a long time and say, how many IOPS are you doing? They're going to hear in their head read and write. But if you ask a NAS guy, a file guy, how many ops are you doing, he will ask you, what operation mix do you have? Because you'll see workloads that do things exactly like we did, 70% stat calls, and you have, or 90% stat calls with almost no reads. And your clients are busy, your servers are busy, everybody's busy, but you're not hardly doing any actual quote-unquote work. You're not doing reads and writes. You're just doing lots of...
Well, you don't do quote-unquote work from the block guy's point of view.
Right,
the file guys say, I'm really busy doing all these stat calls.
Yeah.
And the last one is the definition between megabytes and millibytes again. So I brought in the slide. We actually originally had several slides in this subject. We had to consolidate to keep the time a little bit better. So on this slide, we try to explain it all in one. And the difference between them, just like Ken was explaining, is the difference between power of 10 or decimal. So you see here on the left, so 10 to the third power is 1,000. So then that's when the kilobyte comes in. And then we kept it everything from 1,000 for a little bit easier understanding. But you can say that 10 to the sixth power is megabytes, or 1,000 squared, and so forth. And it's just that. Just use power of 10 to get to the numbers, and they're called kilobytes, megabytes, gigabytes, terabytes, normal terminology that we know. On a binary side, in the computer land, when we had 0 and 1, this is when the binary really came through, we use a power of 2 because it's all it is. It's bits. And when you multiply power of 2s to the same amounts, there is a difference between tebibytes and terabytes. And that difference, ironically, is about 97 gigabytes, which is about 10% of tebibytes total amount, which is significant. And the only point that we're trying to carry across for this presentation is remember which units you're trying to measure in and keep them consistent. And if you see somebody use millibytes, chances are they know what they're talking about. If you see somebody using megabytes, that's a red flag. Stop and think whether they mean real megabytes or they actually were thinking of millibytes and they just used the wrong notation. As long as you equate those terms and you make sure you use them consistently within whatever it is that you're measuring, you're going to be all right. It doesn't matter if it's millibytes or megabytes, as long as they're true to the base.
Well, to that end, I think we've extended it past our scheduled allotted time. I do want to thank the people on the call for joining us today. The questions and comments in the section are phenomenal. You've given us some homework to do to address some of these. A lot of questions came in about the influence of the network on these performance, and I have no doubt that we're going to be doing some additional illustrations about networks and their different network protocols later on. Right. So fear not, there will be more. You have a comment, Mark?
I just want to thank the audience. Thank you very much by participating. We are humbled by the numbers of people that came to the session. I think at some point we had over 500 live viewings, and that's really, really important for us. And thank you very much for your time. Ken?
Yeah.
Completely agree. Thanks.
And we will have, even if we couldn't get to your questions on the air, we will be posting a blog with every question and answer, including some links to additional information for you. We do apologize we couldn't put in a master's course for benchmarking in just an hour, but we are going to be doing additional webinars in the future and going to be covering as many of the needs as you feel are necessary. So without any further ado, thank you very much. Please do not forget to finish your ratings, and I hope you have an excellent day.
Thanks, Jay.
Thanks, Jay.
Thanks, Mark.
Thank you, everybody.
Great job.